So one way to look at these rules are, well, as I'm designing my diagrams, I should be making sure that I'm following along with the rules to this ladder diagram. But in most cases, once you guys leave this module and go into the next one, right when you get into PLC, but then when you get out into the real world again, if you come into this motor control world, any diagram that you guys grab for a machine, it is very likely going to one of two things. Either the machine has a PLC, which most things have PLCs these days, or it was, if it doesn't have a PLC, still the diagram was created with some kind of software. All right, not a lot of people are pulling up a T-square anymore these days and drawing perfect lines and putting lines perfectly across and introducing symbols with their pens. This was done, probably in the 80s, maybe still in the 90s, but I think at some point, once computers started to be a thing, as far as everyone had them, even companies had them, then everybody was just kind of using the computer to structure the diagrams. So a lot of the rules that we're going to look at here are just, if you use a program to create ladder diagrams, it's just going to kick them into the structure. There's not a lot that we have to actually remind ourselves to do. But what this is about is more so how to read the diagram, all right? How to understand the diagram and how it's structured. So let's get into the first rule of a ladder diagram, which if you are highlighting, as I've been suggesting that you do, those first two, well, sorry about that. Sorry, not the first two. Sorry, I thought it went all the way. Just the first sentence here, which gives us the first rule to a ladder diagram. No more than one load should ever be placed in any circuit line between the power lines 1 or L1 and L2. All right, no more than one load should be placed on any circuit line between L1 and L2. But I'm going to kind of restructure that rule. Because first of all, it's a little too wordy. It doesn't have to be that long. Also, it's not using the proper, I would say, the term that I want you guys to remember, which is rung, R-U-N-G. So let's kind of restructure this rule. Feel free to write this out or even just put a note for yourself, which just simplify that whole sentence. One load per rung. That's it. All right, short and sweet, 4 words, didn't have to be all that long. One load per rung. Now, when we see the word rung, what we are associating with the word rung is the circuit line between L1 and L2. All right, that is the definition of a rung. The definition of a rung, now we'll zoom in a little bit, is the line that goes between L1 and L2. That's your circuit. Remember what I had mentioned on Tuesday. L1 and L2 are power. They are the power coming into the circuit. L1 and L2 represent power. They do not represent the circuit. All right, that is a test question. Just letting you know right now. L1 and L2 do not represent the circuit. The circuit is in the across. All right, it is called a rung. All right, just like on a ladder, it's called a rung. So when we see the word rung, we are now being told it's the line that goes across. And so we can have multiple rungs on a ladder diagram. I have been asked before, how many rungs can we have? Endless rungs. However many rungs you need to represent the circuit that's running whatever machinery that we're talking about. They don't go that long because, machines, how complex can they be? I mean, even the most complex robotic system is going to have a lot of rungs, 100, 200 rungs maybe. Well, maybe not 200, but a good 100 rungs for a robotic system that has a lot of motion. Every motion, by the way, that just doing this right here, that's one rung. If this finger goes that way and that way, second rung. So everything that is going to be energized, that is going to cause motion or close circuits or start motors, it is a load and it deserves a rung. So for example, if I have motor 1, 2, 3, 4, 5, 6 that are about to get energized, motor 1 goes on one rung. I should have erased all this. Motor 2 goes on another rung. Motor 3 goes on another rung. Motor 4 goes on another rung. Even if the thing that is going to start all four of them at the same time is one single switch. All right. In other words, the idea is don't put motor 1, 2, 3, 4, and 5 on the same rung. Everybody gets his own rung. So in a system where I have, let's say, 4 motors that are about to get started, automatically that's 4 rungs. Now, if I want to add a green light when motor 1 starts, 5 rungs. If I want to add a green light with motor 2, 3, and 4, I'm going to need 4 more rungs for all the lights. If I want red lights to turn on when the motors are off, 4 more. That's already 16 rungs for 4 motors with 2 lights each. Sorry about that. Green and red, 2 lights each. 16 rungs just for 4 motors with 2 lights each. So if you include anything else, more rungs. So that's how rungs take off on us. Because every single thing that you want to energize, that is, again, a load, that's what a load is, it is going to require its own rung. By the way, I'm going to set up one page here to set up all the notes, because I am going to consolidate a little bit of the way the book is giving us the notes. Just like I did with this one, I'll shorten all of the notes a little bit. And again, you can bring your notes into class for the exam, so you can structure this to help you that way too. All right, so no more than 1 load per rung. I'll finish reading the paragraph a little bit here. For example, up here we have a pilot light being connected into a circuit with a single pole switch. In this circuit, the power lines are drawn vertically. On the sides of the drawing, the power lines, again, L1 and L2 are power. They are the vertical lines coming in. The space between L1 and L2 represents the voltage of the control circuit. So the control circuit is not L1 and L2. The control circuit is the space between L1 and L2, or the rungs. All right, we don't have to read the rest of that. No worries. That's why it's not a very complex system. But they are showing us the incorrect way to do it. All right, let's look at the incorrect way to do it, because it's going to kick us off into the next figure, which is going to show us what to do when we have 2 loads. All right. And I just explained what to do when we have more than 1 load. You're going to need another rung, but let's first take a look at the incorrect way. Here you have a pilot light and a solenoid. You can't put 2 loads in series. All right, that's the other thing. Words, right? Words matter because, again, you're going to take exams and the exam says true, false. You know, loads can be placed in series with each other. Well, that's false. 2 loads cannot be in series with each other. So if I have more than 1 load that is going to go into the same ladder diagram, then we'll go on to the next figure, figure 5-2. As always, holding for a second to make sure everybody can find it. I don't know where these might be the next page right over. They might both be on the same page, or I don't know how the book is structuring it. This is what they're telling us. Loads must be connected in parallel when more than 1 load must be connected in a line diagram. I'm going to finish this paragraph, and then, like I said, I'm going to restructure this note. In this circuit that we're looking at here, there is only 1 load for each line between L1 and L2. We'll talk about it because they are picking up a line or a rung from the center. We'll talk about that right there. You notice that they are picking up that rung from the center. They're not bringing the rung from L1. This is good and this is bad. I'll explain the positives and negatives of that. So in this circuit, there is only 1 load for each line between L1 and L2. Even though there are 2 loads in the circuit, the voltage from L1 and L2 appears across each load to for proper operation of the pilot lights and solenoid. This circuit has 2 lines, 1 for the pilot light and 1 for the solenoid. So the way they're structuring this first sentence here, where it says loads must be connected in parallel when more than one load must be connected in the line diagram, I'm going to change that and simplify that note to this. Extra loads, more than one, require extra rungs. All right. Hopefully that simplification makes it easier to even understand. If I got another load, I'm going to need another rung. Motor 1, motor 2. Motor 1 gets a rung, motor 2 gets a rung. Pilot light for motor 1, that gets its own rung. Now, let's look at the way they've structured this one, L1, L2. At some point, I'm going to start to drop L1 and L2 in my drawings, but hopefully at some point you're just catching on. L1 on the left, L2 on the right. So they have a switch. They're just using a toggle. Well, actually, no, they're using a push button in this sense. Sorry. They have a light. And then they are picking up the circuit from there. And then the solenoid down below that. Good enough. So in this case, this is why I don't like that sentence the way it's structured, and I don't want you to memorize it this way, the parallel. Because, again, I don't know how far we'll get into this chapter today, but we should be able to get into into the 5-3 part, where we get into logic functions. And logic functions is talking about parallel and series, but it's going to be talking parallel and series in reference to the control devices, not in reference to the loads. So in this particular case, yes, the light and the solenoid are in parallel with each other. All right, in a ladder diagram, when two things are side by side, the push button and the light and the light are in series with each other. So if two things are on the same rung, they are in series. If two things are one over the other, go this way, sorry about that, they are now in parallel with each other. So in this particular case, with this type of line diagram, yes, it is okay to say that the two loads are in parallel with each other. But let me give you a for example of when they're not. Here's when they're not. But let me go back 1 second. The reason why they're in parallel with each other is because of that right there. Is because of the fact that we are picking up this rung from the same rung that is feeding that light. So in other words, we're picking up the rung for the solenoid from rung 1. We'll get into the numbers of the rungs. Not too complex. 1, 2, 3, 4. We just count in that order, but we'll get to it. It is going to be coming up as a note here in a second. So here's a second option. Say I got a push button, but now let's say I got a motor starter. All right, we know our motor starter now. At least we're getting familiar with our motor starter. Not going to worry about the overload right now. Remember what I said yesterday. Motor starters have auxiliary contacts on them. All right, again, motors, well, technically just the contactor, but let's imagine the overload was here, so I'm holding a motor starter. This is going to start the motor as soon as this gets power. Contacts close. Motor is now energized. So when I place my auxiliary contacts on the motor starter, as soon as the motor starts, these contacts react as well. I have two normally closed contacts on this. Technically, they're in the middle. And two normally open ones on the outside for a total of 4 contacts. So I can use my normally open contacts every time the motor is going to get energized to energize something else. So in that case, I can use the contact, we'll say normally open from the motor, to energize, let's say, a light. Here is a different way to structure two loads required, right? I got two loads now, so I'm going to need a second rung where I did not pick up the rung from the other one. So now I actually have two rungs. This is rung 1, now this is rung 2. These are not in parallel with each other. I mean, in the broader sense, everything that is one on top of the other can be called parallel, but they're not. It's not the same as when the circuit comes from here and then energizes this light. So because this is not parallel with each other, but we are dealing with more than one load, this is why I don't like the way this sentence is structured. Loads must. No, they must not. I can structure the diagram in another way where I am not connecting them in parallel with each other. So this is why I would prefer that you would understand the note like this. Extra loads, extra rungs. That's all. Because as you learn how to create diagrams and how to create circuits, you'll be able to take advantage of the different ways in which you can wire up a circuit. Now, the benefit, I would say, and here's my reason. I always like, anytime I'm starting a second rung, I like to start the rung from L1. I do not, as much as I can possibly avoid it. All right? Unfortunately, in the case of the one in the book, I cannot avoid it. But as much as I can possibly avoid it, I try not to start the circuit from the center of a rung. And there's a reason for that. In this case, again, there's no real option because I don't have a contact on the light. The light does not come with auxiliary contacts the way motor starters come with auxiliary contacts. So in the case of a light and a solenoid, then yes, there is no other way to do it. I'm going to have to structure it like this. I'm going to have to pick up the rung from the center of the other one. Again, this is only for motor control. In PLC, you can do all kinds of magical things. But here's the reason why I don't like that, is because what this is telling us when that little dot is right there, and for in-person, now that you guys have built a few labs, and I'm sure that you've had this little dot on a line or on a rung, sorry. What this is saying is, hey, this wire that's leaving that solenoid going into rung 1, it doesn't have a home yet. What that little dot in the middle of the rung is saying is find a place to put that wire. Right? You can either bring the wire from the solenoid directly to the push button, or you can bring the wire from the solenoid directly to the light. But you will not splice in the middle of that. This is the thing I want you to understand. That little dot does not mean splice those wires. All right, so let me just clear that up and put it here so that I can work with it in the... When I'm wiring this up and I'm starting to bring my wires from L1, I bring a wire from L1, terminate it at the push button, bring a wire from the push button, terminate it at the motor starter, A1. We'll start to throw in some numbers now. This is universal for all motor starters. No matter the brand, everyone uses A1, A2. So what do I do with this wire? Well, this wire's got to go to one of those two spots. All right, this wire cannot, again, we're not going to cut the wire going from the push button to the motor starter, cut it right in the middle like we do with a regular electrical circuit and splice it with some wire nuts. We do not splice in motor control. The reason being is we need to test the wires, we need to measure the wires to see if there's voltage flowing through for troubleshooting circumstances, and undoing a wire nut can cause chaos. All right, it can disconnect wires, stuff can start to shut off, and now you're creating secondary problems to the mix. So whenever you have a little dot in the middle, you're going to have to find a place to put that wire. So you can bring the wire to the motor starter, or you can bring the wire to the push button. All right, there's the diagram, and then there's how the person wired this. All right, I'm going to say that again so it can be absorbed. There's the diagram, the way it was written, and then there is the reality of what's going on in the field. How was this thing actually wired? And the reason why I don't like the little dot is because I now give the person that's wiring this the opportunity to make that decision as to where to land this wire. And that might not seem like a big deal until you have to troubleshoot this machine later on, and you don't know how they wired it. So now part of you trying to troubleshoot is you tracing down wires. And that is time that you are taking in troubleshooting to trace down a wire where, go back now to how I originally wired this, or designed this. In this set of circumstances, there is no way, other way I should say, for the person wiring this to have done it. These wires can only have gone to L1. This wire from here to here can only have gone from there to there, and the one from here to here from there to there. That's it. So in this case, the way I have this diagram structured, the diagram and the way it was wired match each other. So if you went to troubleshoot this, confidently go, and I know exactly where the wires are going to and coming from because it's exactly how the diagram is saying that they are supposed to go. Again, anytime you place a little dot and you say, hey, we're picking up the rung from there, you are now giving the option to the person who's wiring this to place the wire wherever they want. And they're not going to tell us wherever they placed it. It doesn't get like a footnote on the ladder. Hey, I put it over here. You now just have to go find that thing. So something to keep in mind as you get into this stuff. But that's the reason why. Two things. One, I don't like the loads have to be in parallel. I much rather extra loads, extra rungs, and also I don't like to pick up a rung from the center of another rung. It just creates a little bit of chaos. Now, like I said, there are places and times and circumstances where there's no option. In this particular one, it's no option. But in this particular one, honestly, this is also, I'm being very now critical, just to explain the point of the dot. In this case, this dot is not a big deal. All right, it's just one wire. It's not, 20 wires doing this, so no harm, no foul with this one. Questions on that? Pretty well understood. All right. If we do, feel free. If not, let's look at the next. Let's look at the next one. All right, figure 5-3. So now what we're going to be looking at in figure 5-3 is we're going to be looking at the load and we're going to be looking at the neutral or the negative. In other words, we've been focusing on the L1 side in most cases is what we do. Whenever we're talking about control circuits and troubleshooting and whatever it is we're talking about, in most cases we're focused on the L1 side of the diagram. But this particular node is going to walk, and the next one as well, the next one as well is going to walk us through the L2 side. All right, so first, a load is any device that is using the energy, all right? Converts electrical energy into motion, heat, light, or sound. By the way, these are the only things that electricity is ever energizing. Things that motion, heat, light, or sound. Think about it, and you probably cannot think of another one. If you can, let me know. So let's continue. A load is the electrical device in a line diagram that uses the electrical power from L1 to L2. Now, here again, I'm going to restructure this last sentence, but if you are going to highlight this, only highlight up to here. Do not include the or indirectly to L2 part. Just highlight up to directly. In other words, that sentence would be fine. Control relay coils, solenoids, and pilot lights. First of all, those are the three things that you're looking at here. A control relay coil, CR1, solenoid right below it, and everything is labeled, so you should be able to see that. And the pilot light are loads that connect directly to L2. All right, control relay coils, solenoids, and pilot lights are loads that are connected directly to L2. Meaning, if you're looking at this diagram here, and you notice on the right-hand side of those three loads, on the relay, solenoid, and pilot light, the line goes straight to L2. That is what they mean by directly connecting to L2. Now, we don't have to hang out here too long because the next figure over is going to explain the next part of this. Because you might be thinking, well, how else is there to get to L2? Well, indirectly. But none of these here are indirectly getting to L2. They are directly getting to L2. Let's look at the other example on the next figure, 5-3, where we have our overloads. All right, now we'll talk a little bit about the overload today. Magnetic, now this is 100% correct. Actually, as always, let's highlight the paragraph, not that little picture up there. Magnetic motor starter coils, now yes, 100% this sentence is correct, are connected to L2 indirectly through the normally closed contact of the overload. So I'm going to go back and forth for 1 second. Magnetic motor starters coils indirectly connect to L2. All other loads, control relay, solenoid, pilot lights, trying to think if there's another, oh yeah, timers, but we haven't talked about timers yet. Everything else connects to L2 directly. Direct connection, indirect connection. Indirect because simply it's not going straight to L2. It's stopping somewhere. It's stopping at the overload normally closed contacts. All right. So let's focus on that overload here for a second. Yesterday we were talking about coils. So I'm going to put a coil here. And it doesn't matter. Well, let's do the motor starter because that's the one that's going to have this. Here's our motor starter. Got an overload here on this side, OL, and L2. Let's now place A1 here and A2 on this side. We don't have to worry about the numbers of the overload. Different overloads, but they all have the same number system, the 95, 96, 97, 98, but don't worry about the number right now. So yesterday when I was referencing the coil and I said, hey, this is A1, this is A2. A1, always positive electricity coming to it from a control device of some kind. I'm just going to put a toggle switch for lack of a better switch. Close the switch, send voltage to the coil. But remember what I said yesterday about the coil. The coil is like a light bulb. A light bulb always has the neutral present. You never open and close the neutral. You only open and close the hot on the light switch. So neutral is always there, ready to go. But in the case of a motor control system, the neutral is not directly going to the coil. It makes a stop at a normally closed contact. And remember what I said about normally closed. Normally closed allows flow. Meaning if this thing is closed, and as long as this is closed, the neutral is at A2 ready for when you close the switch on the A1 side. So for those who didn't do code D, because I did go in depth in code D into overloads, you should all that took code D with me remember what overload was, but we'll just do a recap. An overload, and this goes for any load, an overload is when the load itself is generating too much amperage. Now, how can amperage go up on a load? Well, a lot of things can happen that can cause the amperage to go up. First of all, Ohm's law. Voltage goes down. I have a massive voltage drop for whatever reason. Massive voltage drop, the amperage of the load is going to go up proportionally, inversely proportional. But if I drop 50% of my voltage, amperage goes up by 50%. That's an overload. In the world of motors, they're machines that are moving parts. Things are moving around. So things can get jammed up. The machine can get stuck. Something got jammed up in the machine. And now the motor is struggling to turn and struggling. And the amperage is starting to go up and up and up internally in the motor. In other words, it's just simply struggling and creating too much amperage. So motors, and only motors, are a machine, are a control system that has a means of protecting it from that situation. Now, all loads have that, right? The breaker is supposed to trip when too much amperage is on the load, or when the load is creating too much amperage. But motors are not protected from an overload by a breaker. Motors are protected from an overload by the overload. And by the way, this is a relay. Technically, it's an OLR, overload relay. And specifically, the way the overload relay works is, in the event that the overload relay internally is sensing too much amperage on the motor, and we do get to set the overload to a particular number. All right, in fact, let's go and take a quick look. Remember which lecture it was. Was it lecture 8? Let's see what pulls up here. No, it's not 7. Don't think it's 7, but let's go over here to 6. Ah, yeah, here we are. Here's my overload. All right, here's an overload close up, just for students who haven't worked with it yet. Take a look at it. Again, we'll get to this. This is chapter 12, and we'll go into chapter 12 and talk a little bit more about it. But the overload comes with a setting, which you guys may or may not have touched yet. This setting has a little Phillips screwdriver where I can set this dial to 11 amps. I can set it to 13 amps. At 13, yeah, 15 amps. I can set it all the way to 17 amps. Those are the numbers that are there. So this overload will protect a motor that runs somewhere between 11 amps to 17 amps. Technically, I think it's 10 to 18, but we don't have to get into those details. So if I were to set this overload to 13 amps and this motor goes up to 15, 16, 17 amps, this overload pops. All right, just like a breaker, it trips. And so I run the neutral wire, and you guys have already done this, to the normally closed contact and out of the normally closed contact to the A2 side of the coil. All right, inside this little thing in here is a normally closed set of contacts that is always, again, always providing the neutral or the negative to the A2 side. And as long as there's no problem on the motor, your neutral will always be there. But in the event of an overload, we'll go back over to the notes where we're at. In the event of an overload, normally closed contact is now going to open. And when it does, all that happens. Why does the motor stop? The motor stops because I lose my neutral. That's all. It doesn't stop the motor, technically. There's no stopping of the motor. It de-energizes the coil. No more inside magnet. Magnet is now no longer, and so the contacts just let go. And that's what stops the motor. So that's why technically when you press start on the motor, you didn't start the motor. All you did was energize A1. You energized the coil. From there, hopefully contacts are closing and there's power going through those contacts for the motor. If the power's not there going through the contacts to the motor, motor's still not going to start, even though you're pressing start and everything seems like it's supposed to be working. And by the way, this is the only time ever in the electrical world where we will ever see this. A neutral being opened in a circuit. Or a negative, but 120, which is what you guys are working with right now in person. Online is working with DC, but same thing. Never in the electrical world do we ever open a neutral on a circuit. Neutrals are dangerous when you open them. But in a control circuit, since there's no actual amperage running through the control side of things, then there's no harm, no foul, no effect. But it would be as though, right? It would be as though, just to give you an example, I turn on my light, I leave the house, and the light is starting to notice it's got a problem internally. Well, the light can't turn off the switch now. It doesn't have a way to do that. So instead, if the light can just simply remove the neutral from it, just kick the neutral out of there, the switch can stay closed. You'll notice motor stopped, switch is still closed. So that's what the overload is intending to do. The overload is simply bringing the neutral over to the A2 side, and in the event of an actual overload, it simply opens that contact and no more neutral. All right, no more neutral, meaning there could still be power on the coil side. Again, this is not dangerous in most cases, but all right, with all that being said, let's head over back to the note, because it is just telling us there's normally closed overload contacts. So I wanted to make sure we all understood all of that. All right, so magnetic motor starter coils connect indirectly to L2 through the normally closed contacts of the overload. An overload contact is normally closed, and here's what it's saying. Open, if you wanted to highlight this, be great. Opens only if an overload condition exists on the motor. Now, it almost doesn't need to be something that we go into, but you'll notice that in all of your labs, there's only going to be one overload here. All right, we're only ever going to do the one that you see on the first rung, even if you have more than one motor. Here's what they've designed here, because this is a design strategy. All right, this design strategy is this. Motor 1 has an overload, right? It's on right next to motor 1. But you could also run the L2 that's going to motor 2 through the overload of motor 2 and through the overload of motor 1 as well. What that does, and that's what they're doing for M3, they're running the L2 through M3's normally closed on the overload, but also through M2's normally closed of the overload, and also through M1's normally closed of the overload. Meaning that if M1 experiences an overload and M1 shuts off, then M2 kicks off immediately and M3 also kicks off immediately. In other words, this is a design that if any of these motors shut off, the motor below it shuts off as well. All right, for whatever reason, designed that way. You know, if you have, like, let's say this is a conveyor system where conveyor 1, 2, 3, and 4, motor 1, 2, 3, and 4, and boxes are coming from 4 to 3 to 2 to 1. Well, if one shuts off, you don't want these boxes to keep coming from 2, 3, and 4 and just piling up and falling off all over the place. You want if motor 1 goes down, shut everything off behind it as well. So that's a way and a design in which can get that effectively done. Now, the way M4 is doing it is they've just drawn one and then wrote all overloads. And as you can see down here, it says preferred method of indicating all overloads is simply draw one and then put all overloads. So that's why I said in most cases these days, this is kind of an older method, but in most cases these days you're going to see it like this. All right, pausing for questions, follow-ups, and etc. All right, so we got that L2 directly when it's a relay, solenoid, and pilot light, and indirectly only ever with the motor starter. Only ever with the motor starter. All right, there's a couple here that I skip over because they're not necessary. Oh, no, this one is, so we'll pause here. So let's jump over to figure 5-6, probably the largest paragraph in the entire book. Truly, I think this is actually there's maybe one or two more there, but this is like one of the larger paragraphs in the entire book. I like the book either way, it's efficient. Doesn't explain too much. All right. So first let's look at the diagram here and let's get an idea of what's going on. And here, as I had mentioned, you will see the words series and you'll see the words parallel. As I said, this is the chapter that starts to explain that to us. So I'm going to use the note right next to it here only because it's right next to the image, but that note exists down here as well. We'll go find it in a second. That note says 2 control devices can be connected in series or in parallel to control any load. In this particular case, they're saying to control a coil in the magnetics motor starter, but you can do this for any load. It can be a solenoid instead of a magnetic motor starter here. It can be a relay. It can be anything. So I can put things in series or I can put things in parallel. All right, I can put things in series or I can put things in parallel. However, something you have to consider when you put things in series and when you put things in parallel. So let's head over to the paragraph here and break that down. So the paragraph starts, says 2 control devices, in this case a flow switch. That's what you're looking at up here, by the way. Symbols are going to start to be a thing that you don't immediately have to start to get familiar with them. I did post a symbols library to give you an idea, but you know, start to learn these a little bit. Temperature switch, flow switch, foot pedal pressure. They're using 4 different types, so that's good. Not just push buttons. In other words, don't just imagine always control circuits push buttons. This is a control circuit with not a single manual control device. So 2 control devices, again in this case flow switch and temperature switch, can be connected in series to control a coil in a magnetic motor starter. The flow switch and temperature switch, and here's the important part, must close, added, together. They are not writing that here, and it is unfortunate because it is critical. They must close at the same time to allow current to pass from L1 through the control device and finally get to the coil. All right, must close at the same time. Again, as always, I'm going to simplify this note, very long paragraph, but feel free to highlight this as well because it is straightforward. Now, the next one. 2 control devices, in this case, the pressure switch and the foot switch, or foot pedal switch, I've always known it, not just foot switch, can be connected in parallel to control. Same thing, coil or any load. In this case, either. That's the important word here. Important word over here is must close. Again, remember together. They're not giving us together, and I don't know why. They're giving us either here. Either the pressure switch close or the foot switch close, and that will allow current to flow pass through L1 control device all the way up to the coil. All right, don't worry about the end of that. So I'm going to come over here. Whenever you put 2 things in series with each other, devices in series must close at the same time, or I should say not the same time. All right. Actually, I didn't really simplify it. I think we're same length of sentence, so not as short as my other ones, but in my opinion, and it is the correct opinion, no, in my opinion, this is a better way to understand it. Devices in series must close together to energize the load. By the way, it doesn't matter how the device is started. All right, I could have, for example, a normally closed emergency stop. I could have a normally open pressure switch. I could have a normally open temperature switch, and then I could have a normally open push button, and then the load. I'll move this over. And then the load. All of them together at some point. They don't have, that's why I changed at the same time. It doesn't have to happen at the same time, but if my pressure switch doesn't close, you can press this button all day. The load has no electricity. So let's say in this particular machine, pressure has to build and come up to proper pressure. Okay, the switch closed. Then the temperature, whatever it is, the machine has to heat up and okay, it reached the proper heating element. Boom, now you got that. Now, when you press this one, yes, now you've energized the load. So whenever you put things in series together, everything has to close at some point and then finally together so that you can energize the load. And again, this is all about troubleshooting. If somebody calls you over to the machine and they say, hey, I'm pressing the start button, the machine is not working, they know about the emergency stop. Hey, the emergency stop is not pulled. Well, they don't know about the pressure switch and temperature switch inside the machine. You do, because you have a diagram. You pull up the diagram and you go, all right, well, we're pressing the push button and it's not energizing the load. Let me check voltage to see if there's any voltage here at the push button, because when I press it, if there's voltage, I should energize that load. If I find that there's no load, or this is why I always start with electricity first. If I find that there's no electricity at the push button, okay, and this is closed, I could now check over here. Let me go check the emergency stop. Oh, there is voltage here. So voltage here, no voltage here, I know where my problem is. Somewhere in there, something has not closed. So normally open positions are not allowing electricity to flow. Normally closed positions are. All right, there's a little bit of everything that we've talked about this week. So devices in series must all close together to energize the load. Now, in parallel, different story. I'm going to put a comma for correct grammar. Either one can close to energize the load. Either one, because they are in parallel, one over the other, independent of each other. If you put things in series, they now depend on each other. For me to receive electricity, that has to close. Then I close, then they close, and then so on. We are all dependent on each other to get power over to the load. I'll be right back to this. I'll just take a page real quick to show the parallel system. All right, let's say I have a push button, and I'll have a little bit of, I don't know what happened there. Here's my load, another push button, whatever. We can have as many as we want. Electricity, where is it, where isn't it, right? Going into the circuit, going into this push button, going into this push button. Either one now. Any of these. If I press this one, load is energized. If I press this one, load is energized. If I press that last one, load is energized, independent of each other. So anytime things are in parallel, then we have the either or. Coming back over here. All right, should be making logical sense, right? Logic functions, logic circuits, logic of the circuit, right? That's what the ladder diagram, this is why that definition, logic of the circuit, was critical. Questions and follow-ups? How we doing on time? We're good on time. All right, so a couple things. We'll run through these fairly quickly. We don't have to hang out too much on these. These are just like extras, but I, want you to know the extras as well. So we're going to run through the next 1, 2, 3, 4 figures, right? We're not going to, no, we don't worry about that one. Next 4. So starting with figure 5-8. Ladder diagrams come with numbers, a lot of numbers. There's all kinds of numbers on the ladder diagram. Rung numbers and numbers for wires and numbers for where we're terminating our components. So this first one here is talking about whenever you have a normally open contact, all right? This is about the contacts. You'll notice the first sentence here. Relays, contactors, and motor starters normally have, unfortunate that they use the word normally because of normally open, normally closed, but usually would have been better. Relay, contactors, magnetic motor starters usually have, I'm going to rewrite this, more than one set of auxiliary contacts. Again, more than one set of auxiliary contacts. I have attached more than one set to this. I got some open ones and I got some closed ones. The open ones, all right, the open ones, that's the one that they're talking about in this page. If you look at this diagram here, and again, the book for this one specifically, there's no way you can see these numbers, I don't think, on the whiteboard, but the number 2, the number 3, and the number 4 right next to that CR1 on the first rung. What 2, 3, and 4 are referencing is that CR1 has one of its extra contacts, one of its auxiliary contacts is on rung 2, one of its auxiliary contacts is on rung 3, and one is on rung 4. And if you look at rung 2, right, we look at rung 2, there's CR1 normally open contact. If you look at rung 3 ahead of that light, CR1 normally open contact. And I almost want to set this book on fire for doing this number 4 right here on the L1. This is so poorly structured, but fine. I'll accept it because that's not a rung. That is just L1 and they've placed a contact on it, but not to get so upset about things. Just calm down here. But same thing is going on rung 5, CR2, 8 and 10. What is 8 and 10? Well, if you look at rung 8, CR2 has a normally open contact. If you look at rung 10, CR2 has a normally open contact. So these little numbers on the side reference whenever an associated contact to one of the loads is located elsewhere. Because like I said, these ladder diagrams can go very long. Robotic systems, 60, 70, 80, 90, 100 ladders, rungs, even more. So if I have a control relay on rung 3 and there's a normally open contact on rung 80, then you're going to want to know that if you're looking for the things that are associated with rung, that control relay. So it will say it here on the side. Now, again, we're going to run through these fairly quickly because they're just extras. If you look at the next figure, 5-9, same as everything I just said, except we're talking normally closed contact, and now there's an underline under the number. All right, the normally closed contacts, and I'll use this down here just because it's a little bit bigger, has a underline. So if you look at rung 12, 13, whatever the number is, if it has a little line under it, it's telling you, hey, there's a normally closed contact on that diagram. No line, it's a normally open contact. Line, it's a normally closed contact. All right, so underline numbers is what they're referencing here. All right, so if you wanted to highlight something here, I would highlight to differentiate between normally open and normally closed. Normally closed contacts are indicated as a number that is underlined. And I would even add this last one, or this next one as well. The underlined number refers to the line on which the normally closed contact is located. All right, little bitty extras. I don't think we use them or as much, you know, in the as far as, you know, me needing to know that about it, but okay. Next figure, 5-10. This is something that is done after you wire up the motor control circuit, all right? After you've wired up the motor control circuit. The reason why I'm emphasizing on after is because the next figure is going to be referencing numbers that we do to the diagram before we wire up the circuit. Figure 5-10 is after you've wired everything up. After you've wired everything up, because you are now going away, right? Remember what I said earlier with that little dot in the middle that gives the person that's wired it up opportunity to do whatever they want, in a sense. And when I go to troubleshoot it, it's hard for me to find this wire now because I don't know where they went to and from. Same thing with just even having to trace down a wire. If I even just needed to trace down a wire in a motor control circuit, as you are noticing from your labs, we don't use different colors. Every wire on a single ladder diagram is the same color. They're all blue, they're all red, they're all whatever was cheapest at the warehouse when we went to buy the wires today. It doesn't matter. The code book doesn't say it has to be. It just cannot be white or green. That's it. But it can be any color. And we don't use different colors for different things. We use one color completely. Now, maybe they'll use different color wires for different voltages just to have some order, but it's not a rule. You do not have to do it that way. You can make the entire control circuit the same color wire. So how do you even trace that down? It would be chaos to have 1,000 wires, all of them red. Where do I even start from? So for that reason, going back over to 510, there is a reference number, all right, or a reference point number on the ladder diagram. But this is going to be a little bit odd if you're looking at this. Let me just go rewind and read the beginning. Each wire in a control circuit is assigned, all right, that's a kind of important word now, assigned a reference point, not so much assigned a number, but it's assigned a reference point. Yes, the reference point is in the form of a number, but the wire doesn't get a number. In other words, it's not wire 1, 2, 3, 4, 5. It's reference point number 1, reference point number 2. What do I mean by that? If you are looking at this diagram, let's try to understand the numbers. There is 1, 2, 3, 4, 5 here, but it's not in an order. Not in an order that really makes sense. Rung 1, sort of. By the way, you can ignore the 1 and 2 that says wire reference numbers with that arrow. You can ignore that one. But the first one next to L1, it says 1, then 2. Then on the other side of the control relay, 3. But then on rung 2, rung number 1 again. And then on the other side of that normally open CR contact, 4. Hey, where did 4 come from? And then on the other side of the red light, 3 again. And then 1 and 5 and 3 again. And then 1, 6, 7. So this isn't 1, 2, 3, 4, 5. I'm not giving these wires that kind of number. This is a reference point. So what's the reference point? Well, there is an order to it. It's not chaos. But if you look at L1 and you look at all of the wires, or rather I should say all of the rungs that are coming off of L1, every one of them, the first wire is assigned the reference point number 1. Meaning that if you're somewhere in the control circuit, at the machine, at the control panel, at a junction box somewhere where you have these reference numbers, if you see the number 1, that wire is coming from L1. And then number 2, going back up to rung 1, that wire is going from the push button only to the control relay. So this is how I find my wires. The way I find the wire is not actually go looking for the push button and looking for the CR. No. I look for number 2. If I'm worried about is there power going from the push button on rung 1 to that control relay, I'm looking for number 2. Same thing, looking at rung 2. If I'm trying to figure out if that open contact CR is powering up that red light, I'm looking for that wire number 4. I'm going into my control panel and looking for the wire 4. They're all red, so I'm looking for the one that says 4. And now you can get a sense of the order. 1, all of the wires on the left. 3, all of the wires on the right coming off of L2. And then 4, 5, 6, 7, 8, 9. Now they follow an order from there. Reference point numbers. They're a little bit confusing. But of course, you have to wire up the control circuit first, and then you can give the wires their reference point numbers. All right, if we move on now, again, moving on a little bit quick. Actually, we're wrapping up here soon. I told you it's hard to get through this chapter. It's just, we haven't even gotten to 5-2. The next one is before you wire up the control circuit. Before you wire up, and this is the number that you guys are using in the labs. This is different. The other one was a reference point number. This is a manufacturer terminal number. All right, it's the manufacturer's terminal numbers. It's down here, manufacturer terminal numbers. In fact, you can highlight that sentence right there. Manufacturers of motor control components. What kind of components? Relays, motor starters, solenoids, push buttons, etc. Any kind of part that is going to go on a motor control system has this, a manufacturer terminal number. It says here are often, are always. Always added to the line diagram after specific equipment has been identified. All right, manufacturers will include numbers on their terminal connection points. All right, first sentence again, if you want to highlight that one. These terminal numbers are, you don't have to highlight this one if you don't want to, but maybe you do, and at that point just highlight the whole paragraph. These terminal numbers are used to identify and separate the different component parts, coils, normally closed contacts, etc., included in the individual pieces of equipment. So I've been showing you guys an auxiliary set of contacts. You guys have been using a different one for my in-person students, but let me see how close I can go. Upside down as always. There we go. You'll notice these auxiliary contacts are not the same numbers that you guys are using. You guys are using a different auxiliary set of contacts, 56, 57, 61, 62, 71, 72, different numbers. These auxiliary set of contacts here, 13, 14, 21, 22, 31, 32, 43, 44. So this is what they're talking about. They're talking about a manufacturer makes one of these, and they assign a number to the terminal points. Because when you go to build this control circuit, if you didn't have this to associate to the diagram, the way you're seeing it here, right? The 2 and 10 on the sides of the control relay, the 1 and the 3 on the contacts, rung number 2, jumping down to rung number 5, 6 and 5. Also, a real pet peeve of mine is 5 goes on the left, 6 goes on the right, 11, 9, 9 goes on the left, 11 goes on the right. We do try to follow that order. And why? Because look at rung 2, 1, 3. Okay, then you go to rung 5, 6, 5. This is no good. You try to keep an order. I'm going to have a word with whoever designed this book. But at the end of the day, it's fine. All right, we're putting those reference numbers. So this is so I can bring a wire from, and again, when we build our control circuits, we're not just going from L1, let's go to the normally closed contact of the control relay. Well, the control relay has 5 normally closed contacts. Which ones do you want me to go to? Ah, okay, now we have a point. So we're going from L1 to the number 6 contact on the control relay. We're going from L1 to the 11 normally open contact on the control relay. We're going from number 1 to the number 1 contact on the control relay. And that now gives us an idea of how to wire it correctly. Because if not, again, I'm bringing a wire from L1 to which normally open contact of the control relay. If you look down here in this diagram that they're showing us, I have one normally open contact number 3, I have another open contact number 7, and I have another open contact number 9. So which one of these did you bring the wire to? You have to tell me so that I can know, so that I can build this control circuit. Once I assign a number to the terminal point, now I can build the control circuit. All right, we do not have to worry about this cross-reference lines and wires. Don't worry about that. This is just you can look at this later on, but this is just the whole sum of the parts. It has everything. It has a line, cross-reference, wires, manufacturers, and the whole kit and caboodle right there. So we can ignore that one. There is, again, a checkpoint as always with the checkpoints. If you want to fall back later on and answer these, 1 through 4 there, 6 through 7. I'm not sure what happened to 5. All right, there's no 5. Search party for 5. Literally, what's going on? The way they number things in this book is frustrating. 1 through 4, then 6, 7. Forget 5. All right. So you can answer those if you want. Now, it is 8:26. I'm not going to jump into the next part of this, line, diagrams, signals, decisions, and actions. That'll take me a good 10, 15 minutes to break down. And it is the last day of the week for our class, and I think we've talked enough today about everything. So I'm going to stop the recording right